Good day, everyone, and welcome to our course on digital electronics and computer programming using Object-Oriented Basic, or OBasic for short. Over the next two modules, we're going to take a journey through two seemingly different worlds, the world of hardware, where electrons and logic define the boundaries of possibility, and the world of software, where lines of code bring ideas to life. What's fascinating about this course is that you will not be learning these subjects separately. Instead, we will integrate them in a way that mirrors how real-world systems are built, with hardware and software working together in harmony. Digital electronics is the foundation of modern computing devices. Whether you're using a smartphone, a laptop, or a smart home appliance, inside every one of them are digital circuits making decisions in binary, ones and zeros. These ones and zeros are just patterns of voltage, but through clever design, they become powerful tools for computation and control. On the other side of the coin, we have programming, in our case, using OBasic. OBasic, short for Object-Oriented Basic, is a descendant of Microsoft Visual Basic. It allows us to write programs that interact with hardware, process data, and create applications with graphical interfaces. It's easy to read, relatively simple to learn, yet powerful enough for building sophisticated systems. Our approach in this course is to pair each hardware concept with its software counterpart. For example, when we study binary arithmetic in digital electronics, we'll also learn how to perform binary arithmetic operations in OBasic code. When we explore large circuits in hardware, we'll also look at how event-driven logic in programming mirrors the idea of storing and holding information. By the end of this module, you should be comfortable with understanding how binary arithmetic works both in digital circuits and in code. Recognizing different number systems and converting between them. Understanding TTL logic gates and simulating their behavior in a program. Writing basic OBasic code that inputs data, processes it, and outputs results. Relating hardware logic design concepts, like sum of products, to logical programming structures. Before we dive in, remember this: hardware and software are not enemies, they are partners. When you write code, you are essentially sending instructions to hardware. When you design hardware, you're often thinking about how software will control or interact with it. Alright, let's begin our first technical topic, binary arithmetic. Part 2, Binary Arithmetic and its representation in code. At the heart of digital electronics is a simple truth: everything boils down to two states, on and off, high voltage and low voltage, or, in symbolic terms, 1 and 0. This is the binary number system, and binary arithmetic is how we perform operations in this system. In binary, the place values are powers of 2, just like in decimal the place values are powers of 10. So, in binary, the rightmost bit is the ones place, 2. The next bit to the left is the twos place, 2 superscript 1. Then 4's, 2 superscript 2, 8's, 2 superscript 3, and so on. A binary number like 1011 represents 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1 is equal to 8 plus 0 plus 2 plus 1 is equal to 11 in decimal. Why do digital circuits use binary instead of decimal? Because it's much easier to design reliable circuits that only need to distinguish between two states, high and low, than to distinguish among 10 different voltage levels. In practice, a logic 1 might be represented by about 5 volts in a TTL circuit, and a logic 0 by 0 volts. Binary arithmetic in hardware. When two binary numbers are added, the process is similar to decimal addition, except that the base is 2. Here's the rule. 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1 is equal to 10, which is 0 with a carry of 1 to the next column. In circuits, this is implemented with logic gates. And other circuits, even the simplest half-adder, uses an XOR gate to produce the sum and an AND gate to produce the carry. Binary arithmetic in OBasic. Now let's connect this to programming. In OBasic, binary values are ultimately stored in memory as sequences of bits. We can manipulate them using standard arithmetic operators, but we can also use bitwise operators when we want to work with the individual bits themselves. For example, if you wanted to add two binary numbers in OBasic, you could simply do VB, copy, edit. dim number 1 as integer equals and be 1011 binary 1011 decimal 11. Dim number 2 as integer equals and be 0010 binary 0010 decimal 2. Dim result as integer. Result equals number 1 plus number 2. Console.writeLine, convert dot to string, result, 2. Here, the and be prefix lets you write a binary literal. When you run this, it will output 1101, which is decimal 13. Notice how the programming logic is just a higher level way of doing what the hardware does naturally. The CPU inside your computer will still perform the addition in binary, your basic code just instructs it to do so. Why this matters in real systems? In embedded systems, such as microcontrollers controlling a digital lock, you might have to handle binary arithmetic both in the circuit and in the software. The hardware could handle simple bit manipulation through logic gates, while your basic program could handle more complex operations, decision-making, and interaction with the user. In short, hardware binary arithmetic is about designing the logic gates to produce correct outputs. Software binary arithmetic is about instructing the processor to perform those same operations for higher-level purposes. Part 3: Enumeration Systems and Digital Codes. When you first step into the world of digital electronics, you quickly discover that decimal numbers are just one language among many. Humans love decimal because we have 10 fingers. That's not just poetic, it's historically accurate. But computers, and the electronics that make them work, operate in other bases that are much better suited to the way they process information. Today, we'll talk about the big 4 number systems you'll encounter: binary, octal, decimal, and hexadecimal. We'll also explore digital codes, the patterns of binary digits used to represent not just numbers, but characters, commands, and even colors in hardware and software. Binary, the native language. We already introduced binary in the last lecture segment, but let's emphasize this. Binary is based 2 symbols, only 0 and 1. Each position represents a power of 2. In digital electronics, binary is not just a choice, it's the only practical representation of information for physical logic circuits. A transistor can be either fully on or fully off, which maps perfectly to 1 or 0. Octal, the shorthand for binary. Octal is base 8, which means it uses the digits 0 through 7. Why use it? Because each octal digit corresponds exactly to 3 binary bits. For example, binary 101,110,011. Grouped into 3 bits, 101,110,011. Octal 563. This makes octal very convenient when you're reading or writing long binary strings, especially in older microprocessor documentation where octal was more common before hexadecimal became dominant. Decimal, our human comfort zone. Decimal is base 10, using digits 0 through 9. In most programming tasks, especially those involving user interaction, you'll use decimal numbers because they are familiar to humans. But in hardware design, decimal is more of an interpretation layer, the binary is still underneath. Hexadecimal, the modern engineer's favorite. Hexadecimal is base 16, using the digits 0 through 9 and letters A through F for values 10 through 15. Hex is beloved in programming and digital electronics for the same reason octal was used, it's a compact representation of binary. But here, each hex digit maps to 4 binary bits. For example, binary 1010-1111. Grouped into 4 bits, 1010-1111. Hex, AF. This is why, in memory addresses or color codes in software, you'll often see values like 0xF or hashtag FF0033. Digital codes, beyond numbers. In electronics, we don't just store numbers, we also store letters, symbols, control signals, and more. That's where digital codes come in. A code is simply an agreed-upon mapping between binary patterns and meaning. Common examples include ASCII, American Standard Code for Information Interchange, which maps characters to 7-bit binary values. BCD, binary coded decimal, where each decimal digit is represented separately in binary. Gray code, where only 1 bit changes at a time between successive numbers, reducing the chance of errors in mechanical or optical encoders. Unicode, the modern extension that supports characters from virtually every language. Numeration in OBasic. In OBasic, these number systems and codes aren't just theoretical, you can use them directly. For example, VB. Copy edit. Dim binary number as integer equals and B1101 binary. Dim octo number as integer equals and O15 octo. Dim hex number as integer equals and H1A hexadecimal. Dim decimal number as integer equals 26 decimal. Console.writeLine, binary number, outputs, 13. Console.writeLine, octo number, outputs, 13. Console.writeLine, hex number, outputs, 26. Even though we write them in different bases, the CPU ultimately stores them all as binary. The prefixes and B, and O, and H just tell the compiler how to interpret what we typed. Why multiple number systems matter? Let's imagine a microcontroller in a digital temperature control system. The hardware might measure temperature in binary form from a sensor. The programmer might convert it to decimal for display to the user, but store it internally in hexadecimal for easier debugging in registers. Understanding how to fluidly convert between these systems is essential to moving between hardware and software worlds without confusion. Conversion practice in your head. For example, convert decimal 45 to binary. 45 divided by 2 is equal to 22 remainder 1. 22 divided by 2 is equal to 11 remainder 0. 11 divided by 2 is equal to 5 remainder 1. 5 divided by 2 is equal to 2 remainder 1. 2 divided by 2 is equal to 1 remainder 0. 1 divided by 2 is equal to 0 remainder 1. Reading the remainders backward, 100 and 1101 in binary. In code, you don't have to do this manually. OBasics convert dot to string, 45, 2 will give you 100 and 1101 instantly, but understanding the manual method means you truly grasp what's happening underneath. In our next part, we'll explore TTL logic gates, the building blocks of digital electronics, and then see how we can simulate their behavior in OBasic. This is where hardware starts to feel alive, and where your programming skills can help you model real-world circuits without soldering a single wire. TTL logic gates recap. We've seen that TTL logic gates, such as AND, OR, NOT, NAND, NOR, XOR, and XNOR, are the smallest decision units in digital electronics. In hardware, they are made from interconnected transistors. In software, we can simulate them with logical operators in OBasic. The key idea is that both worlds, the physical circuit and the program, are doing the same logical evaluation, just in different forms. From basic logic to complex expressions. While a single gate can perform a simple decision, most real digital systems need more complex conditions. In electronics, we often combine several gates to represent more complicated logic. Two common forms for expressing this are called sum of product and product of sums. Think of sum of product as combining several small rules with OR logic after each rule has been built with AND logic. Product of sums works in the opposite direction, combining several broad conditions with AND logic after each has been created with OR logic. The important takeaway for you is that these expressions allow you to describe very complex decision-making clearly. In OBasic, the same principle applies when you write compound conditional statements, using combinations of AND, OR, and NOT to represent rules in code. Latch circuits, the idea of memory in hardware. A latch circuit is one of the simplest forms of memory in electronics. It can hold a value, a single bit, until instructed to change. Imagine a light switch, you flip it on, and it stays on until you flip it off again. That's essentially what a latch does, but in digital form. In programming, we have similar concepts, variables that keep their values until the program changes them. Event-driven programming, especially in OBasic, often works like a latch. For example, a button click event can set a variable to true, and that variable will remain true until another event changes it. Shift registers, moving data step by step. A shift register is a hardware component that can store a group of bits and shift them left or right by one position each time it receives a clock signal. This is useful for tasks like converting serial data into parallel form or vice versa. In OBasic, you can simulate shifting using bitwise operators. Shifting is common when dealing with graphics, encoding, or even encryption, where you move or rearrange bits to achieve a certain effect. The important point is that shift registers in hardware and shifting operations in software both serve to move data in a controlled way. Digital to analog conversion, bridging two worlds. Not all signals in the real world are digital. Many are analog, like temperature, sound, or light intensity. A digital to analog converter, or DAC, takes a binary value and produces a corresponding voltage or current that represents that value in the analog world. In software, particularly in OOBasic, you might handle DAC values by calculating the digital numbers to send to hardware so that the correct analog output is produced. For example, setting the brightness of an LED or the volume of a speaker might involve computing a value in software that the DAC turns into a real voltage. Memory devices, storing information. Memory in electronics comes in many types: RAM for temporary storage, ROM for permanent instructions, flash memory for rewritable storage, and so on. At the most basic level, they are collections of storage cells that can hold binary data. In OOBasic, memory usage is seen when you declare variables or create arrays. The program's variables exist in RAM while the program runs. Just like in hardware, data in RAM disappears when power is turned off, unless it's stored in a more permanent form. Binary math circuits, hardware calculators. Binary math circuits include adders, subtractors, and more complex units like multipliers. They perform the core arithmetic operations directly in hardware, allowing computations to be done incredibly quickly. In OOBasic, you can perform the same operations in code, but it's worth remembering that underneath your program, the CPU is using binary math circuits to get those results. Multiplexers and demultiplexers, data routing. A multiplexer is like a digital traffic director. It takes several input signals but only lets one of them through to the output based on control signals. A demultiplexer works in reverse, taking one input and directing it to one of several outputs. In OOBasic, you might simulate this behavior with conditional statements or select case structures, where the program routes data or actions based on a control value. Timer circuits, keeping track of time. Timer circuits produce precise time delays or pulses. They are used in everything from blinking LEDs to coordinating communication between devices. In programming, timers allow you to schedule actions, measure how long tasks take, or trigger events after a delay. In OOBasic, you can use built-in timer functions to track time in milliseconds, which parallels the function of hardware timers. Counters, counting events or steps. A counter is a circuit that keeps track of how many times something has happened, for example, how many pulses have occurred on a signal line. In software, counters are simply variables that increase by 1 each time an event occurs. This is a common pattern in OOBasic, where you might count button presses, iterations of a loop, or completed tasks. Analog to digital conversion, rereading the real world. The reverse of DAC is ADC, converting analog signals into digital values that a computer or microcontroller can process. For example, an ADC can take a voltage from a temperature sensor and turn it into a number the program can use. In OOBasic, once that number is available, you can store it, process it, or display it. This is where programming meets sensor data directly. Bringing programming into the picture, OOBasic fundamentals. Now that we've gone through the foundational hardware concepts, let's make sure we've tied them to our programming environment. History of Visual Basic and .NET. Visual Basic began in the early 1990s as a way to make programming for Windows easier, especially with graphical user interfaces. Over time, it evolved into VB.NET, which is built on the .NET framework and supports modern programming features, including object-oriented concepts. Navigating the IDE. The integrated development environment for OOBasic or Visual Basic within .NET is where you write, edit, and run your programs. It includes a code editor, debugging tools, and design views for building user interfaces. Creating simple programs. In OOBasic, you can create Windows Forms applications for graphical programs or console applications for text-based interaction. You can write statements to take input from the keyboard, store it in variables, perform calculations, and display results to the screen. Data types and variables. Different types of data, like integers, floating point numbers, text strings, or Boolean true/false values, are stored in different ways in memory. Choosing the right data type makes programs more efficient and less error-prone. Arithmetic and operators. Just as hardware circuits perform arithmetic using logic gates, OBasic uses arithmetic operators to perform addition, subtraction, multiplication, and division. It also follows precedence rules so that expressions are calculated in the correct order. Closing thoughts for Module 1. In this first module, we've built a foundation that connects the dots between physical digital electronics and their software counterparts in OBasic. We've moved from binary numbers all the way to data conversion, memory, and basic programming techniques. The key takeaway is that every programming instruction eventually becomes a hardware action, and every piece of hardware is ultimately controlled by software. Understanding both sides means you can design systems that are not only functional but also efficient and reliable.